Okay, let's go to gravitation. It's found that for any two objects in the universe, there is an attractive force, and this attractive force depends on these masses and also depends on the distance between the centers of these two masses. This was found by Isaac Newton in this way. The force between two objects is proportional to m1. Also, the force is proportional to m2, and at the same time, is inversely proportional to the distance between them squared, right? That's the distance from one center of mass to the other center of mass. Correct? Perfect. When we combine these factors that are acting on the force, we get that force must be proportional to m1 times m2 divided by r squared. Because they have different units, we need to match the unit, so we need to change this symbol by equals and add a constant. So what do we have? Force must be equals to a constant. We're dealing with the magnitude in this case, times m1, m2 divided by r squared. G is the constant of proportionality. This is the universal gravitational constant. And the value, the magnitude is equals to 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. Right? This is the magnitude, but force is a vector, right? So what should be the force as a vector in this case? Well, imagine that this is the mass acting, or the force of this mass acting on this mass, right? The force is an attractive force, but because this is the origin right here, we have the direction, right? This is the unit vector direction r goes from 1 to 2, but the force is gonna be opposite. In this case, what do we have then? The force, let's say, down by 1 on 2 is equals to negative g m1 m2 divided by r, the distance from 1 to 2 square, times r in the direction of r hat, right? The radius direction, radial direction, correct? Okay, and we have again this is the gravitational force. In general, is gonna be equals to negative g m1 m2 divided by r squared, right in that direction. What about for the Earth? For the Earth, what should be the gravitational force done on object by the surface of the Earth? Well, in this case, we take this, let's say, the test mass and any mass, right? And according to this analysis, we take the mass of the Earth concentrated at its center of mass, right? This is the mass of the Earth, and we create a picture right like this. So we have an object, another object right here. This is one mass, this is mass of the Earth, and the distance is radius of the Earth. And we apply right this formula, or this formula. Look, this formula are for point masses. Okay, perfect. Now, when we apply that, what do we have? Force, gravitational force is equals to, let's find only the magnitude, gonna be G, M would be this one, times mass of the Earth, right? The second one, divided by radius of the Earth squared. Correct? But we found before that the force acting by the Earth on the object near the Earth's surface is just the weight. We found that this force is just the weight, but this force, right, is equals to what? Is equals to this magnitude, but weight is equals to mg. When we compare this mg to this force, what do we have? mg is equals to big G, right? M, mass of the Earth divided by radius of the Earth square. Correct? Now this mass is cancelled, and what do we have? G, right, as a magnitude, its magnitude is equals to big G times the mass of the Earth divided by radius of the Earth square. Correct? Perfect. This is again by the surface of the Earth, and G is constant in this case because it's constant, constant, constant. Correct? And that's the case again when we are dealing with the gravitational field, right? Gravitational field, right, we found before this constant. The symbol is G, correct? That's the gravitational field, and is related again to the gravitational force. So we represent this as the gravitational force equals to m times g. What should be then the gravitational field? This equals to gravitational force divided by mass. Okay, when we substitute this value, right? When we substitute this value right here, or this one, right here, what do we have? We have that now g, the gravitational field, now it's a vector, is equals to a negative g, right, m. This is for the Earth. It's gonna be mass of the Earth, correct, divided by mass, correct, divided by mass times radius of the Earth square. Correct. And what is this? Well, it's found that the gravitational field is equals to negative g. In which direction? Okay, the same thing as before, right? G times mass of the Earth divided by radius of the Earth square in that direction. Correct? Perfect. Now, this one we use this formula, right? What about the general one, this one? Well, in this case, we substitute as this value, right, by this, correct? And we're dealing again with the Earth. This is the Earth, okay? How we can find the gravitational field? Well, we use a test mass. We use a test mass, m naught. Okay, this is the test mass. What happens? Well, this mass is being attracted by the Earth. Now let's move the mass around the Earth. Let's place it right here. Right, it's being attracted. Right here is being attracted. Right, it's being attracted. It's being attracted. Right, at any point. Now, what should be the gravitational field, right, on the Earth? Well, it looks like it's gonna be in this way, right? According to the test mass, it's gonna be attractive. Of course, we can represent also in this way, right? It's gonna be increasing, going toward the center of the Earth. This is G equals to what? Equals to negative G. Let me do it right here. Right here, G is equal to negative what? Negative G mass of the Earth divided by r squared. For any particle right here is gonna be right r. The distance from the center of the Earth to that position. Correct? Perfect. Of course, in this direction. This is the radial direction because it's a gravitational force is a central force, right? Or also it's a conservative force. Correct? Perfect. Now, what happens in this case if we are on the Earth? If we're taking, let's say, the distance from the surface, let's say h, and this is radius of the Earth. What should be the gravitational force, right, or gravitational field at that position? Well, in that case, G, right, is equals to, we can take the magnitude, the G mass of the Earth divided by radius of the Earth plus h squared. Correct? Perfect. And this is again the gravitational field. Perfect. Now let's go to the gravitational potential energy. Let's do it. Gravitational potential energy. Gravitational potential energy. We found in the previous chapters that work is equals to negative the change in the gravitational potential energy. Could be gravitational, could be elastic potential energy. Correct? Also, we can say then that the change in the gravitational potential energy is equal to negative, right, work. But how do we define work? Work is force times distance, or the dot product. Remember, we can also say in this way it's gonna be the derivative. Let's use the integrals. Is equals to negative the integral of force that dr. Correct? Because force is dependent on the distance only. Correct, on the radius, and the distance is a central force. Perfect. Let's do it. So then I'll be from 1 to 2, the same thing up here, right? For R1 to R2. In this case, we have that this is the inner was gonna be final minus initial equals to negative. What is this force? Well, this force is just the force acting right here. This is equals to what? It's equals to Gm. This is for the Earth, m, mass of the Earth, correct? Divided by r, right? R square from R1 to R2, correct? But this is negative, right? This is negative right here. It's gonna be negative, correct? It's gonna be negative. The force is negative, correct? Perfect. So what do we have at the end? It's gonna be what? Again, we're dealing with the integral, correct? We're dealing with the integral. Well, we're dealing with the integral before this. Perfect. What else? dr. Okay, perfect. And then what do we have? This from position 1 to position 2. Okay, so this is equals to Gm, mass of the Earth, correct, times negative 1 over R, correct, from R1 to R2. And this is equals to negative Gm, mass of the Earth, times 1 over R2 minus 1 over R1. When we compare this to this, we can see that in general, the potential energy, right, gravitational potential that depends on R, is equals to negative Gm, mass of the Earth, divided by R. Correct? Perfect, and that's the formula for the gravitational potential energy. Right? Perfect. Now let's see what happens one more time when we're dealing with potential energy, gravitational potential energy. We have these two cases. We know that if we are dealing with flat Earth, well, we found that this is this is a gravitational field, but we're looking for gravitational potential energy. Correct. We take a mass right here. This is gravitational potential energy equals to 0. Lay is gonna be over here, correct? And if this is h, the height, the potential energy is gonna be equals to mgh. Correct. What about for the Earth? For the Earth, right here now at the surface of the Earth, potential energy is equals to, now this takes the value of the radius of the Earth. This is gonna be negative, let me do right here, gonna be potential energy equals to negative G, right? This is the mass M. This is the mass M, right? Mass M right here. M, mass of the Earth divided by radius of the Earth. Correct? Right here, at this position, distance h, what should be the gravitational potential energy? Is equals again to negative G M mass of the Earth divided by radius of the Earth plus h. See the difference? Okay, and that's when we have flat Earth and when we have the Earth right as a planet. We have the difference in the gravitational potential energy. Correct? Okay, perfect. Now, this is above the surface. What about even looking for the force right inside of the Earth? Imagine that the Earth is with a constant density. Let's see what happens. Okay, let's see how's the force inside of the Earth. Alright, okay, let's do it. To explain that, look, we use the concept of the inverse squares law. Let me explain that part. Inverse square law. Imagine that we have a source, could be a light, right? The intensity of light decreases by the square of the distance. The same thing as for force, right, and for gravity, right? Decreases as the inverse of the square of the distance. Okay, perfect. Imagine that we have this situation right here. We have the field going in this direction, correct? And let's take the unit like this, right? This is the unit in that direction. This is one, could be 1 meter, 1 kilometer, 1 centimeter. That's the unit. Okay, let's double this unit. Imagine this is the case right here. Imagine. Now, when that happened, look, this is twice the distance. This is 1. This is gonna be 4. But what about to the intensity? Imagine we're dealing with the intensity. Well, because this area is the same as this area, actually the intensity is gonna be 1 over r squared. Correct? For the same area. The same thing happens when we're dealing with the gravitational field, right? Or the gravitational force. It follows right the inverse squares law in this way. For example, look, imagine that we have a spherical shell, right? It's a spherical shell like this. Imagine spherical shell, correct? And we're looking for the force at the center of this spherical shell. Well, we take masses, like for example in this case this mass, and this mass acting on this mass at the center of this spherical shell. Correct? Because they are the same distance and the masses are the same. This is m and this is m. This mass is acting on this one with this force, and this mass is acting on this mass with this force. Because the distance is the same, right? We're dealing with the same masses, so the forces are the same but opposite directions, correct? So the net force inside of this spherical shell is 0, correct? Now, imagine that we move this mass to this position, to 1/3. Imagine the same thing. Okay, let's use the same figure, correct? This is the line, one more time. Inside, now divide this by 3. What happens if the mass now is placed right here, m naught? What should be the net force acting on this mass. Okay, let's do it. The same thing as before. Let's take this section of mass, correct? This one right here, and this one right here, acting on this mass. If we take this as the unit, as we did before, this is 1. This is gonna be, or we can take this R1. Look, R1 from here to here is R1, but from here to here is gonna be twice R1, correct? This R1 is just twice R1 right there. Perfect. Now let's compare this to this analysis, the Mr. law. If we take this to be the unit, this is the unit of mass. Right here, when we double the distance, it's gonna be 4 times the amount of mass as before. Like in this case, if we take this to be the unit of mass, this is the area, area. We multiply the area by 4 when we double the distance. The same thing happens right here, right? If instead of the area we take the mass, the unit mass right here, in this section, in this case it's gonna be 4 times that unit mass according to this rule, this law. Correct? Perfect. Now let's see what is the force. The force done on this mass because of this amount of mass. It's gonna be what? Force, let's say case 1 is equals to G M naught divided by R1 square. What about the force done? This is the force in this direction, let's call it F1. What about the force done by this mass on this test mass? Let's call this F2. Okay, let's do it. So F2 is equals to Gm naught. Now what is the total mass? 4m divided by, what is the distance now? It's 2r1. This is actually equals to r2, right? R2 is twice r1, correct? But it's gonna be square. And what do we have? Well, it's equals to Gm naught m divided by r1 squared, right? The force are the same in their opposite direction, so the net force at that point is 0 too. So inside of a spherical shell, right, the net force is 0, right? Gravitational force. Okay, now let's take this analysis to find the gravitational force inside of a solid sphere. Now, a solid sphere with density constant, right? Constant volume density. Okay, imagine that we have again a the same thing as in this case. We have a hole inside, right? Imagine, well, before that, imagine that, well, let's make a hole. Okay, let's make a, let's drill a hole. Imagine that we place a mass right here, inside. Correct? What happens? Well, we can create something, a shell like this one, right? Let's create a shell like that. Correct? And according to this analysis, we can place it right here, just to match this part. Okay, we can place it right here. Okay, the same thing. Just at this point. So it's found that this shell, look, this shell right here produces or gives a net force 0 right on this mass. This is my naught, and this is the total mass. Correct? So look, in this case, okay, this is the mass right here. Let's position as the mass. Okay, look, in this case, this mass right on this shell, to simulate this right here, we can place this again, this mass right here, the same thing, correct? And it's found that the net force inside of this shell is gonna be 0. So the same thing happens right here, right? Imagine this is a shell, so inside is 0. So the only force acting, then we can call this this volume, right? MA, for example. So in this case, this is right MA, the mass, and this is right M naught, correct? So we can take the center mass for this mass, right? And actually, this is the mass that is pulling on this mass, right? it's gonna be this amount because the rest is cancelled out, right? Like in this picture, using the inverse squares law. Great, and we call this the distance r, right? This is the distance from the center, right? R, and this is the radius of the sphere with density, or volume with density, spherical volume with density constant. The density is constant. Okay, with constant density. Okay, perfect. Now let's apply the force done by this mass on this test mass. Okay, this is equals to G, what else? Let's take only the magnitude for simplicity, m naught times ma over r squared. Correct? But what should be ma? This amount of mass. Look, when we use density is equals to the density for this mass, this volume is equals to ma divided by 4/3 pi r cubed, right? And the density for the whole sphere, which is the same because it's constant, the density is equals to the total mass divided by 4/3 pi r cubed. Because these two are the same, what do we have? We have that ma over 4/3 pi r cubed must be equals to the total mass 4/3 pi the radius of the sphere cubed. When we solve for ma, well, this is equals to the total mass divided by the radius of the sphere times cubed times r cubed. Now, let's substitute this value right here, and what do we have? This is equals to G m naught, what is ma? Ma is equals to the big M, correct? Divided by r cubed, right? This is little r cubed, and this is r squared right here, correct? Perfect. Now, what should be the magnitude of the force then inside of the Earth? It's gonna be equals to G, right? M naught. Now let's take this to be the mass of the Earth in case, right, the density is constant. It's a special case, correct? Divided by r radius. We use the radius of the Earth in this case, radius of the Earth times r. Radius of the Earth cubed, root cubed times r. And that's gonna be the gravitational force right inside of the Earth. Perfect. It's gonna be, this is the magnitude equals to G m little m, mass of the Earth divided by radius of the Earth cubed times the interior radius. Correct. The same thing happens to G. What should be G inside? Well, G inside is gonna be, we cancel this one, gonna be G m, right? Mass of the Earth over radius of the Earth cubed. Correct. Perfect. But look, what do we have right here? Right here we have that this quantity is constant. This is constant. One more time. Imagine that this is, we can use that one, right? This is the whole right here. We place a mass m right here, and this is mass of the Earth. This is the case again when the density is constant. Actually, the density of the Earth is not constant. Okay, perfect. Now let's see what happens. Well, as you can see, this is constant, this is constant, and the radius of the Earth is also constant. So the end force, gravitational force, equals to a constant times r, where C is equals to, it's gonna be equals to G m mass of the Earth divided by r cubed. Also look, also we can use this quantity, right? G right here. Correct? We can use it we can use it, right? We can use G, correct, this G right here, correct, you want to. Okay, then what do we have? So this is, the point is that this is the behavior of the force, right, inside of the Earth. But look, when we compare this, in general, right, if we're dealing with force, it's gonna be negative, right, negative, perfect. But we compare this to the spring force equals to negative kx. Look, they have the same form. So, but what is the force? What happens when we have a spring? The spring is gonna be oscillating, right? What happens if we place a mass right here on this drill hole through the Earth? Well, it's gonna behave as the spring, right? So this mass is gonna be oscillating right back and forth, because they have the same form. Correct? The same form. Also, we can calculate the period, right? The period for this mass inside of the Earth. Let's do it. Let's do it. For example, what do we have? We have that omega is equals to square root of k over mass. This is for the spring, okay? It's for spring, right? But omega is also equals to 2 pi frequency, right? And then when we compare these two, also a frequency is equals to, right, the inverse of the period. When we compare this to this, what do we have? This is for the spring, okay, for the spring. So for the spring, we have that the period is equal to 2 pi the square root m over k. This simply happens to gravity, correct? Because they have the same form, so we expect to have the period equals to 2 pi square root mass divided by c, right? This constant right here, where c is equals to that amount. Let me do right here. Okay, let me do it right here. So we have that the period for this object, right, inside of there, right, it's gonna be oscillating. It's gonna be equals to 2 pi, correct, times the square root of mass. What should it be? C is gonna be G mass of the Earth over radius of the Earth, correct, square, cubed. Correct, what is this? This is equals to 2 pi the square root of R radius of the Earth cubed, correct, cubed, divided by G mass of the Earth. Also, look, we can use this quantity, correct? We can use this quantity right here. Look, this is equals to 2 pi the square root of mass divided by Gm, gonna be m, correct? G divided by R of the Earth. And what is this? So this is equals to 2 pi the square root of radius of the Earth divided by G. And that's gonna be the period. You can use this formula or you can use this one. The answer is the same, correct? This is easier because we have only one and this quantity, which is radius of the Earth. Right here we have to use radius of the Earth cube, right, G, and mass of the Earth. So it should be better to use this equation, right? And that helps us to find the period, right, of a mass inside the Earth in case we have a hole. It could be to the center or could be right at any position, correct? The period is gonna be the same time. Perfect. So what do we have then? Let's take to graph these formulas. Let's do it. Let's do it. So what do we have when we're dealing with gravitational potential energy, right, and so on, correct? So for example, we have the force right? If we're dealing with gravitational force that we found before, right? Force, remember this is the Earth right here. That's the Earth, correct? So how is, let me do it this way. This is the Earth. Okay, this is the Earth, correct? This is the Earth. And imagine that this is the axis, right? It's gonna be in the x direction, and it's gonna be the force. But inside, how is the force inside? We found it before. The force inside depends on the distance, right? It's gonna be in this direction, correct? So inside is gonna be what? Negative. Inside gonna be any more room? Okay, right here. Negative is gonna be this formula right here, correct? It's gonna be this one's gonna be negative g m, right? Me, right, radius of there over radius, right, of the Earth cubed. Right here on the surface, right here on this surface equals to what? It's gonna be the force is equals to negative gm mass of the Earth divided by radius of the Earth square, correct? Because at this distance, this r becomes radius of the Earth, and we have that quantity, correct? Perfect. What about outside? Well, outside we have, correct, we can use this, okay, in this way, because I'm gonna start from here, correct? Well, the right here is gonna be decreasing, it's gonna be the distance in this way, correct? But later, right here is gonna be in this direction, right, like this, correct? Let me do right here. It's gonna be again in this way, correct? In this way, and then it's gonna be like this. This is inside, and this is outside, correct? This is the force, gravitational force. This is distance r, correct? This is again inside, and this is outside, like this. And it's negative, that goes that why it goes in that way. When we take that as the magnitude, we're taking the magnitude. What do we have in this way, and then in this way, right? This is the force, and this is distance r. This is when we take the magnitude, right? Right here is taking the direction negative, and right here is magnitude is positive. It is proportional to r, correct? And then it's inversely proportional to the distance square, correct? Perfect. It's the same behavior for r, for g. What is the same behavior for g? Correct, the same behavior, the magnitude. Okay, great. And with this, let's finish this section. This is half of this chapter, gravitation. And let's continue right on this analysis in the next video. Okay, thank you and see you later. Bye.